So in this video, we'll try to solve the problem which we saw in the port of FreeRTOS. So in the port of FreeRTOS, we have created two tasks, task 1 and task 2, but we saw that the UART prints were coming as a garbled prints. Okay, let me show you that problem first, and then we'll try to solve that problem in this video. Okay, so let me just open the PicoCom. Now I will power up the RPi. First we'll see the problem. Yeah, so we are getting U-boot logs. Now let's copy that kernel 8 image to RAM. After this we'll read some data and then jump it. We'll just try to see first what was the issue. Okay, and after this we'll try to solve it using one of the OS component. Yeah, so here you can see, right, that hello came from task 1. After that the print is started coming from task 2, and we are not getting the complete prints of the task 2. Okay, so this one is what we'll try to solve it. Okay, let's let it be running. So in FreeRTOS we have I have downloaded the FreeRTOS user manual guide. You also can get it from the internet. Okay, so this is that reference manual for FreeRTOS. Here you will get all the APIs of the FreeRTOS which can be used in the FreeRTOS kernel. Okay, so if you go down here, we have a lot of functions, and in this guide actually they have explained in a very easy way with example also how these APIs can be used. So here we are jumping to directly the Semaphore. So what we'll try to do, we'll try to create a Semaphore, and using that Semaphore, whoever would have acquired that Semaphore will print that on the UART and then release it, so that there will not be any contention of the hardware. So we have only one mini UART which we have built up. So whoever acquires that Semaphore will have exclusive access to that UART to print its logs. Whichever task, okay, has acquired it will have exclusive access to that UART, and after printing it, it will release it. And if some other tasks has to print again on UART, he should acquire that Semaphore again and then print it. Okay, so that's what we are going to do in this video. Okay, so let's see this Semaphore create. Okay, so this is that API which we have to use for creating the Semaphore, and after creating the Semaphore, next would be we have to basically see how to acquire the Semaphore and release the Semaphore. Okay, so let's go to our code, and let's go to our code. Okay, so this is the code base where we are building that FreeRTOS, then threads created. Okay, so before creating the tasks, I will basically create a Semaphore. Okay, so let's see how to create it. So for that you have to import the semaphore.h. okay, we can take example also from here. They have given the example also. So we have to create one Semaphore variable. Let's copy it. Okay, and so this is that Semaphore variable, and after that we have to use that x Semaphore binary create. We are creating a Semaphore which is only of which is only one. The count is only one. Why? So you can create a Semaphore which is when suppose you have multiple UARTs, right? So suppose you have two UARTs, so you can create two Semaphores, and basically this is used for any resource management. Okay, based on how many resources you have, those many resources, based on that you can create either binary or a counting Semaphore. Okay, I am creating a binary Semaphore because I have to work with only one UART hardware. Okay, after creating it, now this Semaphore will be available to the threads. So suppose task 1 wants to print it, so he should be able to first get this Semaphore. Okay, so can you see here, the problem here is in line number 53 I am creating this Semaphore as a local variable. Instead of this, I should define it this one as a globally. Okay, then that Semaphore handle will be available to other threads also. Okay, so let's put it here. After that now let's go to the task 1, and inside task 1, before doing the printf, he should acquire the Semaphore. So we have functions to acquire the Semaphore also, but since we have created it, we have to also check whether it has been successfully created by the RTOS kernel or not. To check that, we have to basically do a conditional check. If that semaphore handle which you have passed it to the semaphore create binary, if it is coming as a null, then kernel is not able to create that semaphore, else it has created the semaphore. So let's use this for, if any, for the creation check, and then we will proceed. So let's, wherever we have created, we will check whether this is created successfully or not. Okay, yeah, so okay, that is fine. So if that semaphore equal to null, then we can print semaphore creation failed. Okay, printf failed to create semaphore. Okay, and no need to create while one. Yeah, we can create, otherwise we will try to acquire it, else it has been created successfully. Okay, that also will print here, semaphore created successfully. Now after this, since we have already put a check whether it's a created or it's failed, now we'll try to basically acquire this semaphore. For that we have that kernel is giving us the API to basically acquire the semaphore and release the semaphore. So let's go to the index again. So here let's go to the semaphore section. Here we have created using this semaphore create binary, and after this we have two functions. One is x semaphore give for releasing the semaphore, x semaphore take for acquiring the semaphore. So by default, if you see this function, whenever it is created with the resource available, means first someone should take it. Okay, that also we can read it here. So this macro remains in the source code compatibility. Use the semaphore create binary. Okay, x semaphore create binary. Okay, macro creates a binary semaphore. The semaphore must be explicitly created before it can be used. Okay, that is fine. Semaphore cannot be created because of insufficient heap memory available for FreeRTOS to allocate the semaphore data structure. That is also fine. We are trying to find whether whenever it is created with an available or it's created with acquired. See, semaphore can be acquired by any task and can be released by any other task. So there is no ownership involved in case of semaphore. Okay, so we can, if we are not able to find, then basically we'll try to do that experiment. A binary semaphore used for synchronization doesn't need to be given back after it has been successfully taken. Okay, task synchronization is implemented by having one task or interrupt give the semaphore and another task take the semaphore. Does not need to be given back after it has been successfully taken. The task synchronization is implemented by taking one task or interrupt give the semaphore and another task take the semaphore. Okay, so I think okay, whether it's available or not, directly not available, but anyway in thread we have to acquire it first and then release it. Okay, so that's what we are trying to go we'll try to do in this one. So what was the syntax for acquiring it? So x semaphore take. Okay, so let's go there first. X semaphore take. Yeah, so this is that API which we have to use for acquiring the semaphore. Let's take the example how to do this. So here the take can be with 0 wait time, or take can be with infinity wait time. So here there is we'll go with the try to take the semaphore with infinite timeout. Okay, so for that this is with 10 ticks timeout. If within 10 ticks the semaphore is not available, it will basically release it, and then it will it will not wait for that semaphore and it will execute next. Okay, but our requirement is we'll take it with infinite delay. Okay, so port max delay. Okay, this macro basically will take to wait indefinitely. Okay, this is what you can see here also. Okay, so let's first use this x semaphore take, and then 10 will update with that port macro. Okay, so x semaphore take, and this 10 we will replace with okay, so whenever x semaphore take is there, then only we will print this function, else we will just do delay. Okay, so but we have to, and once it is acquired we have to release it also. If it is acquired we have to release the semaphore. Okay, x semaphore give is for releasing that semaphore. Release will be immediate. If we have acquired it, we can release immediately. Now the next would be using this v port delay. Okay, so let's take that macro we just now saw here only, right? So we port max delay, so this will wait indefinitely for that semaphore. Okay, Okay, if it is true, then it will print the hello from the task 1. Now the same thing we have to do in the task 2. Okay, so let's copy it and print inside task 2. Okay, this print will remove from here because we want to do that printing only when it acquires the semaphore. Okay, after acquiring it will should basically release it. So this X semaphore should be available to both of them. Yes. Okay, apart from this we have to include where the semaphore has been defined, so that also has been given in the example. So that header function is available in semaphore.h. okay, so let's copy this and put it in our code. Now we'll try to build it. Just first do the make clean. We'll first do we are inside play with bits. Yes, ls here we have make file, so let's make clean, and after that let's build it. Okay, so what it is trying to say that these functions are not available, semaphore.h is not available. So let me see why semphr.h is not available. It's available, but in function implicit declaration of the function x semaphore take, did you mean x semaphore handle? X semaphore take, X semaphore give and create binary is not available. Okay, even after including that semaphore.h. Okay, I think a problem is with this, we have copied it wrongly. Okay, let's try make clean and then make it. Yeah, so we are able to build it. Now let's load this, copy this binary to our TFTP boot, and then let's do SCP of this, and then we'll load this binary to the RPi. Okay, so let's plug in and plug out and plug in. We should see what happened. Yes, we are getting the input console now. Now let's load the binary which we have built, okay, using TFTP. So this kernel is now transferred to the RAM at this location. Let's read some of the bytes, and after that we will jump to the core. Okay, so here what has happened, we are not getting any prints after this. Okay, so basically this task also is not getting created. So before that only we are trying to create this semaphore, but what is happening, it is silent hung. It's not telling whether it's not able to create whether it is inside this semaphore null or whether it has created successfully. Okay, so yeah, we'll try to see whether this dynamic creation of a semaphore is allowed in the FreeRTOS config.h. okay, FreeRTOS config.h, here generally we should have set it as 1 for creating the semaphore. Okay, if we have not set it as 1, then basically the definition of that semaphore create will not be included in the FreeRTOS kernel, and whenever it will try to reference it, basically it will not get, and will get the silent hang. So the same thing would have been made clear in this user guide also. So let's see inside user guide which flag it wants us to set so that semaphore APIs would be available. Okay, so let's go to the start of this semaphore section, and from there we will try to find is there any flag which we need to set. X semaphore create binary, X semaphore create binary. Okay, so let's go through this to find out in FreeRTOS do we have to set any flag for getting this binary in the for getting this API in the kernel. Okay, creates a semaphore, summary has been given, small amount of RAM. Okay, if that is not the cause, then another thing can be key, it's not getting enough heap to allocate, basically to allocate that X semaphore variable handle. Okay, so it can be any of the two reasons. First we'll try to see the macro reason. If then RAM is provided by the writer application. Okay, we are not using that static, so basically user doesn't need to provide that, allocation will happen from the heap. User doesn't need to provide the memory for the semaphore variable from the RAM. By default we have used the create binary without static, so it should be given from the heap. So this is fine. Let's try to find but do not have subtle difference. This makes binary semaphore better choice for implementing synchronization between tasks or interrupt and tasks. Okay, binary semaphore, semaphore create count. Okay, so inside this FreeRTOS config.h we should, this definitely should be set as 1. So this is one thing we have to check it. So let's check this one. Yeah, so we have set it as a 1, so dynamic allocation is allowed. Now apart from this, any other handle we need to, macro we need to set it. That's what we are trying to find out. So here mutex static allocation must be set to 1 for this function to be available for static one. Any other flag he wants to be set, it's available. Counting static, that is also fine. So it is taking about support. Okay, this one is also taken care. Now we are trying to find any other flag it is asking for semaphore to be available. If that would have been case, it would have been cribbed. If you use static now, it will do that check during compilation, but since we have used the dynamic creation, that's why we don't know what will happen. We will only get the error during your runtime. Okay, so here also that flag is almost fine. Okay, this we went inside semaphore, sorry, it's not semaphore, recursive mutex, semaphore delete get count, mutex holder. What we can try, right, we can try, instead of going through like this, we can try searching okay, which flag we should set in FreeRTOS for getting the semaphore APIs in the kernel. Okay, let's go there, let's find if anything we can find out. Semaphore, so we have only one this, so include underscore x semaphore. Include underscore x sema. So we have this for mutex holder and this mutex. Okay, apart from that there is nothing. Then the problem comes why this is happening. Other way is if we are not able to get this, then we have to basically do that static one, but just I'm trying to see. Okay, maybe heap is not there, that's why it is not able to take. Okay, let's find inside a image file whether we have this variable defined or not in the list file. EL1 entry, it is coming in EL1, and yeah, this semaphore is there, so it is able to get the value inside the BSS section because it is uninitialized, so that is fine, that should be fine now. But why we are getting silent hang? Other thing which I am thinking in this is, after creating, we are directly trying to, by the time this print comes, that is fine, but we are trying to if it would have gone here, definitely this print would have come, otherwise definitely it is going to this semaphore created successfully, and by the time we are getting the print, maybe since we are trying to take it without releasing, because both of the threads will try to take the semaphore without releasing, that's why it can be one of the reason for the silent hang. So let me try to do experiment by giving immediately after creating, let's give that semaphore, okay, so that it will be available to any of the threads, and whoever thread takes it, it should release it and then proceed. So here we have created after creation. If it were after creation, we let's give that semaphore, and then the task can be created so that the task can acquire it. Okay, let's try building this. Okay, so we have built it. Now we'll transfer this kernel image. Okay, so we are here now. Let's try to see, let's try to test our image. tftp081234 kernel 8.img. Okay, let's read some data, and after this we will jump to that location. Go to 0x234. Okay, so now, yeah, so that was the problem. So now you can see the clear prints from each of the threads. So whoever will acquire the semaphore, he will print all his, he will do the prints from using UART, all the characters he will print, then only it will release it, then it will be available to the other tasks. Okay, and then other task will start printing. So this is how this is how the semaphore is created and used. Okay, so we can clearly see right now we are not seeing garbled prints from some prints from the task 1 and some of the prints from task 2. We are seeing the complete prints from each of the tasks. Okay, so this is how we use it. Okay, so this is task 1, there is no other change, and this example also I will commit to the same repository that is available in the GitHub. Okay, so now this is how we should use the semaphore. This I have shown you the uses of semaphore between tasks, how to synchronize between two tasks. The same thing can be done between a task and an interrupt. That also I will try to show you in the next video. So thank you so much.